Definitely.
Wow. Geez, shots fired.
What if you just have 8 ideas?
Truth is the truth.
No, you're fired.
Then we can float around in chairs.
Silence.
No, you can't.
Oh wait, this is finished.
We need silence. Please.
You never finish telling us about school. Like, no, remember you were saying.
Oh, you were talking about school and about
Oh
caring.
yeah, about why he shouldn't like just skip Friday.
Yeah, you never.
Oh, yeah.
The conundrum.
I thought we
It's
started talking
simple.
about thesaurus.
Conundrum. There
It's
we go.
simple.
We're back to it.
Thesaurus or something?
Okay, so number 15, it's really simple. Okay. In your life, throughout your life, you will purchase a lot of different things. You will spend an enormous amount of money over your lifetime to pay for all kinds of things. Food, entertainment, automobile, transportation, housing, clothing, right? Entertainment. I can guarantee that of all the things you'll purchase, if you ever bought something and you paid thousands of dollars for it, like literally thousands of dollars, and somebody said, oh, never mind, we decided not to give it to you, you would be upset. You would not stand for it. You wouldn't say, oh, I'm fine, sure, take my money, I don't care, don't give me anything back. Like, I'm happiest if you just take the money, don't give me a thing.
Oh, that's terrible.
But there's one product where everyone celebrates when that happens.
College.
Education.
Yeah.
Like, you pay money, and if they don't give you anything, you're like, thank you. That's what I was hoping for, is to pay you money and get nothing in return.
Oh,
But I do.
I don't spend money.
Oh, wow, this is rough.
But we're learning how to problem solve getting out of school.
Well, I do wonder if, like, I know, like, I've talked to my dad, he paid for his own college, and he said, like, in college, like, he had a new appreciation when he was the one paying for his classes, and he had tons more motivation than in school when it was just paid for him,
Yeah, well,
So I think
his
there's
parents paid for it, and so it's harder. Yeah, because his parents paid taxes.
Oh, sure, right.
Yeah, so-
But I mean, I think
Oh, yes,
once
for
you
sure.
pay it, you have, like, a greater appreciation.
Oh, yes, that's the whole. That's actually the whole dilemma, right?
Yeah.
Is, hey, should we make people pay for their own education so they value it more? But then, of course, that has the problem that those who really do want education and can't afford it, that's a problem, So anyway, here we go. 15. It's an integral. If you could pick up your calculator, okay? It's an integral. If you could pick up your calculator and plug it in, you're done. Like there's nothing hard about that. They're never going to ask you to do that. Okay, never going to ask you to do that. I can also guarantee you something else, having spent 15 years in industry. Just because you have access to information doesn't mean you can produce a thing. Just because you can go on Google and Google all day long and gather information does not mean you have any value to the company. Zero. Facts. Rebut all you want. Okay? It is absolutely true. Okay?
It's not.
Because if it weren't true, you could hire people to just sit there and Google all day, but you can't. It doesn't make any money. It doesn't produce anything. So. All right. We need to find the value of the integral, but we can't use our calculator because for your goal, which is to pass the AP test and prove to somebody that you know something, okay, not that just you sat in a seat for a year, which is of no value. So you're getting me a little fired up. Look, silence. Okay, on the AP test, 20% of the problems cannot be solved unless you use a calculator. The other 80% you are required to solve without the use of a calculator. So we're now into the 80% realm. So to solve this integral, you can't use a calculator, so what we have to use is the most tested formula on the entire AP test, the fundamental theorem.
That's the fun.
That is the fundamental theorem of calculus.
How many fundamental theorems do we have?
We have one. It is known as the fundamental theorem of calculus.
Oh wait, we're just.
Brother. All right.
They just looked at me.
Notice within the integral up there, there's a formula of such.
That's the D of T.
There's a formula here. What Ryan is remembering is that we could write the fundamental theorem a little differently. We could have written this, and the theorem would still be valid. I will often say that a big problem in math and science is too many students think the symbols have this like inherent meaning. Symbols don't have any meaning until you assign meaning to the symbols. So you shouldn't look at the fundamental theorem and get stuck on, oh, this is the fundamental theorem. No, that's a version. This is an equally valid version of the fundamental theorem. Here's another valid version. These are all valid versions of the fundamental theorem. Not that valid? It's a rough day, man. Time to increase the difficulty of the test. Okay.
There isn't a test.
Time to create a test. All right.
We really gotta stop talking.
It's all up to you guys.
Making them mad.
Look. The key idea is this. It's not really that crucial that you think of the fundamental theorem as being the integral of f prime. What's crucial is you be thinking that the fundamental theorem is the integral of some formula, okay, some formula, but that integral is equivalent to the evaluation, is what I'll call it, of the antiderivative of the formula. So here we have f prime in blue. Over here we have f. In this version of the fundamental theorem, we have v here in orange. And then we change color to black. We've got x over here in black. And on this last one, we got brown as small f. And then we've got yellow as capital F. And the key thing that all of you must remember is the green and the blue have a specific relationship. The orange and the black have a relationship, and the brown and the yellow have a relationship. So Matthew, what's the relationship?
They're all derivatives and derivatives.
Which is which?
So, which one?
Start with this one. How is blue related to green?
Blue is the derivative of the...
Perfect. Blue is the derivative of the green. The fundamental theorem associates those two things. Integrating the blue, get the pen to work, integrating the blue produces the exact same result as evaluating the green, like finding values of the green and then just comparing them. Blue is the derivative of the green, green is the antiderivative of the blue. Same is true for the items you see here. The orange is the derivative of the black. Therefore, the black is the antiderivative of the orange. Same thing here. Small f is known as the derivative of large f. Therefore, large f is the antiderivative of small f. Questions? Please.
Is like the uppercase and lowercase a typical use? Like
It is a typical use, but it is not a rule. So what you see me writing here doesn't have to be so, but they do use this on the AP test fairly often, so you do have to kind of get used to it.
So uppercase would be the
Antiderivative. But that's not a rule, that's just sometimes they'll do that. Please.
Will problems ever use like the rules on this sheet and then the rules on our green sheet from the past, like on the same problem kind of?
Yep. Absolutely. Okay. So let's keep going here for a second. So for example, if I write this,
1/2 squared, which is 1 squared.
actually we talked about that, the derivative, so we're good there. Okay, so any question about how antiderivative and derivative are related in the fundamental theorem? Awesome. So if I want to solve this integral up here, and I don't have the option of picking up my calculator to solve that integral, what I'm going to do instead is take advantage of the fact that if I go find the antiderivative of this blue formula, and then I plug into that antiderivative these two values, I can find the value of the integral. That's my goal. Question? Cool, next thing. All right, so let's erase this and start over. So on your paper, what you want to write down is, we're going to do kind of a little problem within the larger problem. So you're going to write the antiderivative sign, not the integral sign. Please.
Sorry, when on our paper you mean like on a separate paper?
On separate paper. Do not do it on the pink. So that's not the integral symbol.
What?
That's the antiderivative symbol.
I beg to differ.
What?
Simple.
That looks the same.
That one's
If
good.
there are limits, we have an integral.
Okay.
If there are no limits,
Uh,
we have an antiderivative.
Looks like a pear.
Simple.
Through the lies of Jedi, bro.
Okay? Some textbooks will say that with numbers we have a definite integral, without numbers we have an indefinite integral. To me that's more confusing. I like the AP style, which is numbers means you have an integral, no numbers you have an antiderivative. So I need to find the antiderivative of this. Because the fundamental theorem says, if I can find the antiderivative of what I am trying to integrate, right here, then I don't need to do an integral at all. I can just use my formula for the antiderivative. Please.
What if I just like did the fundamental theorem of calculus and just plugged in B and subtracted plugging in A?
Like, tell me what you want to write, Nathan.
So I just did 1 over 2
So you're going to
squared.
start with that, right? Let's write it down. Hold on.
So integral.
So you're saying the integral from 1 to 2,
Yep.
1 over x squared dx is the same as
1 over 2 squared. Oh, that's 4.
like
1
that.
over 2 squared minus 1 over 1 squared.
So what you would be doing is you would be saying that the fundamental theorem is the following. The integral from a to b of some formula is actually exactly the same thing as the exact same formula with the two limits plugged in.
I fell into a trap. No. That's why I bought it.
So is that the fundamental theorem?
No,
No, but it is a common mistake. Yeah, that doesn't work.
I'm a little confused on how you got rid of the 1 and the 2. Is it just because it's an antiderivative, or like where did they kind of go?
So what I did is I said, I want to find the value of this integral, right? You with me, Lucas?
Uh-huh.
Okay, but I can't use my calculator, so I can't find that. So the fundamental theorem says, think of that blue thing as f prime. It doesn't have to be f prime, just think of it as f prime for a moment. The fundamental theorem says if you're trying to integrate this blue formula, and you can't because you don't have a calculator, do something else. Pay attention to equal. Equal means same thing. So it says, don't do the blue at all. Let's go do the yellow. But to do the yellow, I have to have a formula for f. So how is f, Lucas, related to f prime?
Oh, so you're finding the antiderivative of f prime.
Perfect.
Oh, okay, that makes sense.
Once I have the antiderivative of f prime, the rest is easy.
Okay.
Fair? 2 more, it's a good call.
So once you find the antiderivative of f prime, then you'll be using the right side of the equation of the fundamental theorem in order to solve the left side.
Right, because remember, you don't think of equal as this becomes this. You think of equal as, hey, these two things are the same. How can I use that? So how am I going to use it? I want to find this. Sorry. I want to find this. I can't. So I quit. I said, no, let's go find this instead. Let's go find f. How do we find f? The antiderivative of f prime. That was bad. The antiderivative of f prime. Come on, stupid board. The antiderivative of f prime. Don't talk. Concentration must increase. The antiderivative of f prime is f. I'm thinking of this as f prime. It's not really f prime. I just think of that temporarily. So I need to find the antiderivative of that. That's why I'm saying I'm doing a problem within the problem. Go. So just like over here, if I'm trying to take the derivative of x to the fourth, I must apply an operator to that formula. The operator is d divided by dx. And this tells you to apply the green rules to this. Agreed? No different. This symbol combined with this symbol are telling you to apply the antiderivative rules to that.
So without the dx.
Without the dx, it has no meaning. It's meaningless. Just like this has no meaning really. Like we have no use for this, at least from what we've learned so far. That doesn't mean anything. Like we can't do anything with it. If we do this, now we have rules that allow us to do something. Same thing over here. 2 points. Anybody else? Okay, next thing. So, here we go. I need to find this antiderivative. The only way in this class, the only way ever to find an antiderivative is with a formula. There is no other method. If you can't find a formula, you can't do it.
How did they find the formula?
Beyond the scope of this class. So,
Who came up with all these?
many people over many years. It wasn't all at once. It was over time.
For this problem, would you use the power rule or the ln rule?
So with antiderivative rules, they must be a perfect match. So the ln rule says 1 over x, right? Because this is 1 over x squared, that won't work. It must be 1 over x.
It just has to be straight.
It has to be a straight match because
What
we're
if it
using
was 2 times that? Then it wouldn't be possible.
a 2. There's a rule.
1 over 2x.
Don't talk. Okay, a rule that is not on your blue sheet because I didn't feel like you needed me to write it down is the same rule that you had with derivatives, which is the multiplying constant rule, meaning you can always pull out a multiplying constant. So that's not a big deal. Also, the add subtract rule for derivatives is the same as it is for integrals. So I didn't write it down. Okay. Sure. All right, look. So don't miss this. Hey, it's a common mistake. That's why this is a trap right here. Okay, it's not 1 over x. So the ln rule doesn't work. It's very different than the green rule sheet. If you look at your green rule sheet, you'll notice every rule is like g of x to the n, meaning you can have pretty much anything. It's because of the chain rule. We don't have really the same ability with antiderivatives. So the power rule on the green sheet says, anything to the n. So it can be anything. Here it's not that. The rules, you look at the rule sheet, it says 1 over x. So that log rule only works for 1 over x. So then, oh please.
So there are only like 10 different problems there could be, and it would just be different numbers for x. No, x would see.
There are
numbers for
techniques that we will learn that allow us to manipulate something that doesn't appear to fit a rule so that it actually will fit a rule. So it's not a different rule, it's like a method to get us to a rule. And we'll talk about that, not today, but another day. 2 points.
So
Please.
for this one, would you think of it as x to the negative 2?
I have to. Because as written, it doesn't fit the power rule. But like Henry just said, I can rewrite this to say this is the same as the antiderivative of x raised to the negative 2 dx. Now I have a perfect match right here. So Ryan will help me here. Does that yellow box match that yellow box perfectly?
Yes.
As long as you choose n to equal. We'll talk about that in a minute. As long as you choose n to equal negative 2. 2 points for Clara. Questions?
Why does it say like
Because if n equals negative 1, x to the negative 1 is the same as what? Right, and then you use the ln rule.
Negative 1 plus 1 is 0. And
So if n is negative 1, the power rule does not work, because what's negative 1 plus 1?
0.
Oh! So did they come up with the power rule after the L?
I actually don't know the history. Please.
Do we know C yet?
We do not. C is simply a number. unknown to us, but we just keep track of the fact that there's some number. It could be 0, might be 5, -2, I don't know. So next line, we figured out that this yellow box here is the same as this yellow box,
Why is C in every single one?
which means it is equal to this brown box. I'll tell you why C is there in a second. So Grant, how do I rewrite this yellow box here differently according to the rule over here? What do I write, Grant?
Write it
No one talks so I can hear.
x to the -2 plus 1. And then all that over 2 plus 1.
-2 plus
Oh,
1.
maybe sorry, 2 plus 1. And then plus c.
Plus C. Questions? Okay, C will be treated 3 different ways. If you are simply finding an antiderivative, look here, come on, look, focus. If you're simply finding an antiderivative, like in, say, problem number 17, you'll notice that every single answer says plus C. The reason for that is super simple. I'll show you why in a second, but if you're just finding an antiderivative, there'll be a plus C, guaranteed. If you are, in some cases, asked to find like sometimes they'll give you a way to find C. Like let's keep going here for a second. So writing this a little more compactly, the denominator there is -1, but dividing by -1 is the same as multiplying by -1. And that's x raised to the -1, which is the same thing as 1 divided by x. So our new formula up here is really more easily written as -1 over x plus c. And if we kind of go with what we talked about at the first, we might think of that as being f. So we thought of this as being f prime.
Oh, when you do plus C minus C.
We thought of this as being f prime. It isn't f prime, we're just kind of thinking of it that way. This is therefore what we would call f, the antiderivative of f prime. Please.
So is like the reason that we can have the C and don't know what it is because if we're doing like derivatives, like you have the constant and like you just don't do anything with it?
That is perfect. So if I take the derivative of f, I'm applying the ddx operator to both halves here. 2 for Nathan. If I use the quotient rule really quickly, I get bottom times derivative of top is 0, minus top times derivative of the bottom will be -1, all over the bottom squared, which would be x squared. Nathan, what's the derivative of the plus c?
Just nothing.
0.
So why do we need the plus C?
Because you don't know for sure that it wasn't plus 10. Because, Ryan, what would be the derivative of a plus 10? Right. So that would still work. Like the whole idea is to make sure you're getting a nice complete circle. You started with the formula 1 over x squared. You found the antiderivative of that formula to be -1 over x. Therefore, the derivative of that formula has to be what you started with, and it is. It's a complete and perfect circle. If you don't have plus c, like this might have been plus 10 or plus 20 or minus 5 or whatever. Any constant will complete the circle. But if you're really trying to find this formula for f, you have to consider that it might not have been plus 0.
So
Wait,
how would you
one at a time. Go
You
ahead.
can't try to find f of a number with the antiderivative. You don't know what C is.
Oh, that's very good. We can't really find f of a specific value. Now, sometimes they'll give us some information like this. They'll say f of, we'll make this pretty easy. They'll say f of 1 is equal to 5. So Nathan Rumler, how would I use this information to find what c's value actually is for a given situation?
Well, it'd be like -1 over 1 plus c equals 5.
Nice, I go -1 over 1 plus c has got to equal 5. Therefore, -1 plus c has got to equal 5.
So C is 6.
C must be 6. Ah, sorry. So that's the second way they'll expect you to treat C. They'll say, now, if we give you some information, you can go find C for a given situation. Question?
So how do we do the fundamental theorem if we don't have the C?
Here we go. So we have our f. It's not really f, but we'll just call it that. So we have our antiderivative here of what we were trying to integrate. So now, new page. 21, what page is that? 21. 22. So we have our original integral, which was 1 to 2, 1 over x squared dx. The fundamental theorem says, rather than trying to integrate this formula here, let's go find the antiderivative of the blue, which we did. So write that down. The antiderivative of the blue was just -1 over x plus c. So we take -1 over x plus c, and we need to plug into that formula two values, 1 and 2. That bar means plug into this formula those two values. Just some new notation. Questions?
You don't do like the first one, the slides.
No. This is the best way.
Really?
So,
But that's the same thing as the FTC.
yeah, so like, in fact, do that for me, Grant. Sorry, Ryan, my bad. How do I write this out here? Like, I want to take this formula, plug in a 2, and then subtract the same thing with a 1 plugged in. So tell me what to write.
Just -1 over 2.
Pause for a second here. So I got -1 over 2. Keep going.
Plus C.
Keep going.
And then minus everything from -1 over 1 plus C.
2 points for Ryan. I made a mistake on purpose. Who can see it? All who can see the mistake. Who can see the error? Common error will cost you big. What's the mistake? Let's go, Henry.
Well, you didn't put parentheses around the second formula, so C.
I have to have parentheses because I must indicate that I am subtracting all of it. If you saw that, give yourself 2. Henry gets 3. Questions? That's the fundamental theorem. Look at the formulas, how they match up. The blue is related to the yellow. Let's go to Clara. Clara, how is the blue related to the yellow?
That is f prime of x and f of x.
We can think of it that way. Slightly better to just think of it as the blue is the derivative of the yellow,
Yeah.
and therefore the yellow is the antiderivative of the blue. If you think that way, it's better for future problems where there really isn't any f or f prime. 2 more. So we take the yellow, we do exactly what Ryan said. We take the yellow formula, plug in 2, take the yellow formula, plug in 1, and subtract. And Matthew, what happened to the C?
It went away.
Subtracted to 0. So it didn't matter. So 3 cases. If you're doing an antiderivative, you just write plus C, you're done. Sometimes they'll ask you to do something to find the value of C. That's what we did over here. We actually found the value of C. Third situation is you're doing an integral and the value of C doesn't matter because you are comparing 2 different values of the antiderivative, so the constant is irrelevant. So I get -1/2. That'll be +1. Final answer is +1/2. Everyone, please grab your calculator. Do a little exercise that will make your brain make a connection and remember the connection a little bit better than it would if you didn't do it. Take out your calculator, plug this into your calculator, and verify that you get what you expect to get.
It's actually.
So when you're saying that this C is irrelevant, when you're like, it's because it's just kind of like C minus C.
Yeah, think of it this way, Adam. We're taking a value of f compared to a different value of f. But the way f is calculated is by adding a constant. So the difference, the C is irrelevant. So. Questions, please, sir.
Is there a way to get an antiderivative on everything? Like, I know we can't use it.
You can actually use so the Inspire has the ability to find some antiderivatives. I've never used it myself very much to know how useful it is. They design problems on the AP test so the Inspire is not advantageous. It doesn't really help you. With math software, they have algorithms that can find antiderivatives as well. Anybody else? Cool. All right. So let's do got a couple minutes here. So go to number. Let's stop. Any questions here? Cool. Go to number.